In today's video, we will be discussing about chemical kinetics. Chemical kinetics is a branch of chemistry which deals with the study of speed or rate of a reaction. So what does rate of a reaction means? We'll see it. Change in concentration of any one of the reactants or products per unit time is defined as rate of reaction, and it can be considered that for a reactant forming product P, rate of reaction is given as decrease in concentration of reactant with respect to time or increase in concentration of product with respect to time. Increase or decrease, that is change in concentration. So delta R can be written as R2 minus R1 and delta P as P2 minus P1. So this R2 minus R1 is nothing but delta R, and similarly P2 minus P1 is nothing but delta P, that is change in concentration of reactant and product. R is reactant, P is product. The negative sign associated here indicates that the concentration of reactant decreases, and the positive sign indicates that the concentration of the product increases. Then unit for rate of reaction, it's given as mole per liter per second. So let us consider what are the factors affecting the rate of reaction. They are concentration of reactants, presence of light, catalyst, surface area and temperature. So how concentration affects is, greater the concentration of reactants, faster is the reaction. Presence of light, it provides the necessary activation energy and the reaction starts, and it is for photochemical reaction. Catalyst, it increases the speed of reaction by decreasing the activation energy. And surface area, greater the surface area, faster is the reaction. And about temperature, if we consider temperature, the rate of reaction becomes double for every 10-degree rise in temperature. The temperature coefficient is defined as the ratio of the rate constant at two different temperatures which differ by 10 degrees Celsius, and its value lies between 2 and 3. So we'll see the problems based on this. Next is order of reaction. So order of reaction is defined as the sum of the powers of the concentration terms in the rate law, or experimentally determined rate law also we consider. So order of a reaction can be either 0 or 1 or 2, etc. That is, it can be a whole number, or it can be also fraction. Then next, if we consider molecularity, it is defined as a number of molecules of reactants taking part in a chemical reaction. And remember, it can be always, it is 1, 2, 3, or it is always a whole number. It can neither be 0 nor a fraction. Next, we'll consider how temperature affects the rate of a reaction. So it is given by Arrhenius equation. It is a quantitative relationship between rate constant and temperature given by the equation K equal to A into E raised to minus EA by RT, where K is rate constant, A is Arrhenius factor or frequency factor, EA is activation energy, R universal gas constant, and T is temperature in Kelvin. The equation can be also written as ln K equal to ln A minus EA by RT. Ln is nothing but log to the base E. So log to the base EK, log to the base EA minus EA by RT, or log K to the base 10 equal to log A to the base 10 minus EA divided by 2.303 RT. So these are the equations which we can use to calculate the activation energy. And to calculate activation energy at two different temperatures, the equation used is log K2 by K1 equal to A divided by 2.303 R T2 minus T1 divided by T1 T2, where always remember T2 is greater than T1. Next is collision theory. So collision theory, a equation obtained is K equal to P into Z into E raised to minus EA by RT, where P is steric factor and Z is collision frequency. Collision frequency is the number of collisions taking place per second per unit volume. And we can even consider that according to collision theory, if the molecules have proper orientation and proper activation energy, only they can form the product. So this was regarding the collision theory. Next is concept of activation energy. The excess, it is defined as the excess energy which must be supplied to the reactants to undergo chemical reaction, and it is taken as the difference between threshold energy and reactant energy. Activation energy and threshold energy are two different concepts. So we see here activation energy is given as a difference of threshold energy and reactant energy. Next is integrated rate equation. So in your NCRT we have derived it zero order integrated rate equation for zero order reaction and first order, that is K equal to R naught minus R by T, and for first order reaction it is K equal to 2.303 by T into log of R naught by R, where K is rate constant, R naught is initial reactant concentration, R is final reactant concentration at time t. Even in first order reaction, we see that K equal to 2.303 by T log R naught by R, where K is rate constant. R naught is initial reactant concentration. R is final reactant concentration at time t and T is time taken. Half-life period. Half-life period is the time during which the concentration of the reactant is reduced to half of its initial concentration. For a zero order reaction, T half is equal to R by 2K. For first order reaction, T half is equal to 0.693 by K. And for any order reaction, T half is given as 1 divided by concentration of R naught into N minus 1, where N is order of reaction. And to calculate unit for any order reaction, unit equal to concentration raised to 1 minus N by T, where N is order of reaction. So let us consider a zero order reaction. If it is a zero order reaction, N value becomes equal to 0. So N value, if it is equal to 0, 1 minus 0 divided by time second. So mole per liter per second is a unit for zero order reaction. Similarly, if we consider first order reaction, so if it is first order reaction, N value becomes 1. So 1 minus 1 divided by second. So concentration raised to 0 is 1 divided by S, so it's per second. So we'll solve the problems based on these concepts, multiple choice questions in the next video. Thank you for watching.